be introduced to them. So let's talk about the 32 crystal classes. Speaking of it, so this again is based on the morphology, the shape of the crystals, not specifically the atoms. However, you can use those atoms and build them up to some of these shapes. It's sort of like point groups. But for crystals. I know Lily knows what point groups are. Katie, did you ever talk about point groups yet or no? Okay. They're basically a group of symmetry elements where a point does not change. There's symmetry. We'll say a family of symmetry elements where a point does not change. When you get to group theory, this is really important, classifying symmetry. For chemicals in physics, orbitals can only overlap with the correct type of symmetry and the correct type of energy, so it prevents things from happening there. Spectroscopy or spectroscopic arguments associated with symmetry are very important. You can rule out possibilities with symmetry, and in some cases, you're mathematically bound to maintain that symmetry in some cases. Came to particle collisions. There are some symmetry operations that are permitted or not permitted by the standard model. And if you go beyond those standard models, you can find way more instances where symmetry is important. Okay. So we're not going to go over all the point groups, but we are going to go through some of the symmetry so we understand what those symmetry elements are. I'm not asking you to be an expert and completely identify everything based upon them, but I do expect you to understand what those symmetry operations are. Okay? So how do we determine? One, we got to determine the outer shape of the crystal, and we have to determine all symmetry elements. So determine shape of crystal. 2, determine all symmetry elements. Okay, and how do we determine all these symmetry elements? We do it systematically, and we do it based upon the crystal viewing direction. Viewing direction. So there are many ways that we could look at the crystal. We've elected to pick a specific direction that we look down, to call that the standard viewing direction. I'm going to give you a table with some of the stuff in here. Oops, we got our crystal class. Actually, we'll say crystal system. It's better. Holographic viewing direction. These tend to be along certain symmetry axes. What are the different crystal systems we have again? That I do want you to know. So name a crystal system. Yeah, triclinic. What else do we got? What was that? Hexagonal. Yeah, we'll worry about that one in a bit. Monoclinic. What else do we got? Yep, orthorhombic. What else? Yep. Trigonal. There's Joe's hexagonal. And then last one, best one. Cubic. Rhombohedral can sort of fit in these two. Okay, triclinic. Which one, what do you know about triclinic systems? Almost no symmetry, very limited symmetry. There is no agreed upon crystallographic viewing direction. It usually doesn't matter because they have horrible symmetry. For monoclinic, it's either B or C. We're going to put a little star. We'll worry about what that star means at a later date. Orthorhombic, we can look along A, B, or C. For tetragonal, we look along C, A, or the 1, 1, 0 direction. Don't worry what that is right now. We will talk about that. Trigonal is either along the C or the A axis. Hexagonal is along the C, the A, or the 2, 1, 0 direction. And cubic, cubic tends to either be C, because all the cubic points, it really doesn't matter what axis you look along, the 1, 1, 1 direction, or the 1, 1, 0 direction. Ugh. Okay. That really does that mean anything to anybody? Okay. That's completely okay. I don't really expect it to. The important point to know is that they differ. So what I'm going to pass out to you guys are two tables. There's an international table of crystallography. There's also another handout that shows some pictures of some crystals. Oops. I got to get another table. I have an extra one. There you go. Aiden, I owe you a table. Because I can't find mine. Oh, here it is. There you go. Enjoy a table. There's a bunch of pictures in there, but what you can see is they have specific... let's look at the one with all the pictures of the crystals. In the top corner, it gives you an idea of what the point group is, where that's the special name of those families. Lily, do you recognize any of these? Okay. C2V, what molecule has C2V symmetry? That was a while ago, right? So, water has a C2V symmetry.
Oh, yes.
Yep. So some of these crystals have parallels to molecules, but what the important point is there are two ways to represent that. So if you look at, man, that is super fuzzy. It's not just my eyes, right? No. Okay, I'm sorry. Let's look at quartz, which has a D6 under hexagonal. So there are the Schoenfly symbols that typically look like this. And then there are these other, what are we going to call them? These other crystallographic ways to represent those point groups. So you might see D6 to talk about quartz, or you might see 622. A trained crystallographer or chemist knows to look at these and say, oh, I know exactly what symmetry elements are in here. Okay. Like for example, there's a C6 rotation. I can rotate this system by 360 divided by 6, and I get the same structure, and there's some mirror planes in there along with some other rotations. Okay? All right. So what we need to do now is we said we have to determine all symmetry elements and all unique symmetry elements. And then the final thing that happens is all crystals with the same set of symmetry elements are considered to be of the same crystal class. So all crystals same symmetry operations. Okay. And that's how it is generally done when determining the crystal classes. People who are really good at this, especially gemologists or people who cut crystals and stuff like that. If you ever go to, there's a gem show that happens in Buffalo. I go every year at the Hamburg Fairgrounds. There's people there who will know this to the T. I don't know this. But the reason for that is they're not really focusing on the atoms or the atomic positions. Being chemists and physicists, the most important thing to us are those positions. However, when this science started experimentally and then theory kind of followed after the fact, and so people were interested in this, shooting x-rays at stuff and seeing what sort of diffraction patterns they got, which is amazing. They used that information to eventually figure out electron densities and then where atoms are. Are there any questions about this one? Okay. So remember, we're trudging through. We started with our 7 crystal systems, or excuse me, yeah, crystal systems. Then we introduced more symmetry, and what did we arrive at? Yeah. We tossed in more symmetry, we got 32. Yeah. We're going to toss in more symmetry. Does anybody remember what the last one's called? Yep, 230 space groups.